So every object in the universe attracts every other object by gravity. Okay. This is the universal gravity, or the law of universal gravitation. And what this means is that no matter what, we can figure out the amount of attractive force between objects, whether it be like Susie or Sally Joe versus Billy Bob or something like that, or just two objects in general, like the planet Earth and a books. And you can actually figure out how negligible that force is between two people. The law of gravity, at least. So the force of attraction is directly proportional to the product of their masses. That means we're multiplying the masses together. And inversely proportional to the distance. So the farther we are, the less gravity that there will be. So the distance between their centers squared. So it's not just distance, but it's the distance squared. If you were in Chem 2, they talked about this in Coulomb's law, except it looked a little bit different, okay? So for gravity, it would be some fundamental constant, capital G, m1, m2 over r squared. So if you're in Chem 2, you're just like, oh yeah, this does look somewhat familiar. This does look very similar to it, okay? And that's because we have the two attractive properties, mass times mass, instead of charge here, okay? So let's do an example problem. And to make this example problem easier, it says solve for the acceleration due to gravity on Earth, given that the distance of Earth, the radius, and the mass of Earth. Why don't we just do this towards and find the force of a 1 kilogram object? That's probably the easiest way to do this. So maybe a 1 kilogram book is the other object. So where is the book going to be on planet Earth? Is it inside the core? No. It's on the crust. And so if this book is on the crust of the Earth, that's why we care about the radius, because it's the center to center distance. Okay? We can pretty much neglect the distance between the center of the book and the crust of the book. Okay? That's going to be like 1 meter. But this is 6,380 kilometers, right? So that 1 meter is going to be pretty much negligible, because this isn't even in meters. This is in kilometers. Let's go ahead and convert this to meters. 6,380,000, right? Or 6.38 times 10 to the 6th meters. Here's our master equation. F equals G m1 m2 over r squared. And G is always 6.67 times 10 to the negative 11. It's convenient because it rhymes. And so we have 6.67 times 10 to the negative 11 times the mass of the Earth, 5.98 times 10 to the 24. They told us that in the problem. We're going to use the other mass, M2, to be a 1 kilogram textbook. And the radius gets squared. So not only is it 6.38 times 10 to the 6th, but that gets squared. Try it in a calculator. And the answer, if you know, you know. So what did y'all get? 9.8. Y'all got 9.8? And this was because we used a mass of 1. If I was just to solve for, this was in newtons, if I was just to solve for everything besides this, if I was to leave that unknown, we could say that the acceleration due to gravity, right? We can divide the mass on both sides and say that the acceleration due to gravity is equal to G times the mass of the planet divided by r squared. Okay? Because we canceled out the secondary mass, the mass of the object. We could multiply that in, mass of the object, and it would make sense because F equals ma on both sides. All right. So that is another equation right there. If I'm looking for the acceleration. Okay. Number 1, let's look at the examples. Number 1 says, what gravitational force does a 100 kilogram lead sphere exert on an identical sphere 3 meters away? You've got to be careful because I did give you 1, 2 variables right there, and g is known. And so even though we just solved for this equation, which looks convenient, it isn't this equation. We're going to back up to the master equation, F equals g m1 m2 over r squared. We have 2 masses. How are we going to change and manipulate this equation this time? What does it tell us about the 2 masses? They're the same. So if I know that m1 equals m2, I could say F equals gm squared. That's different than the acceleration equation. We still have both masses, but they just happen to be the same. All right. And so we have 6.67 times 10 to the negative 11. And then we have the mass, which is 100. And then we're going to multiply that by another 100. Then we're going to divide that by 3 squared. Don't forget to square that denominator. Okay, that's the most common mistake, is forgetting to square that denominator. And if you did your math correctly, I think you should get the answer that's already posted on the sheet for the example problem. Double check. Alrighty, so number 2. A girl has a mass of 60 kilograms on Earth's surface. What would she weigh at a height above the Earth's surface, 1 Earth radius? So she's not on the Earth. She is in the sky, probably in outer space. I think that's past the stratosphere because we're more than a couple miles away. We're like 1,000 miles away. We're 3,000 miles away. 4,000 miles away. Right? So we have radius, and then we have another radius. So she's way out there. How could we claim this? We could call this 2r. Okay. So force equals g m1 m2 over the distance that she is. I'm going to just put d squared because we have the radius of the planet, which is just 2r squared. The mass of the planet. What planet is this? So that's 5.98 times 10 to the 24. I'm pulling this out of my memory because you're going to need to memorize that one for this test. And then the mass of her. Oh, 60. And then we're going to divide that by 2 times 64. 6.4 times 10 to the 6 squared. That's just the 6380 rounded, okay? You can round it a little more, right? It's fine. Yeah, I would memorize the radius of the Earth for this test and the mass of the Earth for this test, just to be safe. They are numbers on, I think they are numbers on the AP formula chart, but I haven't given you the AP formula chart ever. Okay, so we got 147 as our right answer, 147 newtons. And again, her mass doesn't change. What would her mass be there? 60 kilograms. It doesn't change. She's made up of the same number of protons, same number of neutrons. One easier way to do this. What's the easier way to do this now that you know that this times times just one of these squared would have been what? 60 times 9.8. If she's twice the distance away, how much is the force going to be? Inverse squared. Not half, a quarter. So if she's twice the distance away, the attractive force is going to be a quarter of what this times her 60 times 9.8 would be. I think it's like 588, right? And so this is a quarter of 588 because she's twice the distance away. If she was 3 times the distance away, her force would be 1/9, right? 3. What's 3 squared? And then you flip it over. So if she's 4 times the distance away, 1/16 the force. Good. Okay.